So I'm going to give a series of 4 lectures. You doing okay on the sound? Okay. A series of 4 lectures on proof theory foundations. And Bob already set me up to some extent in terms of the first lecture. You can think of this as being titled Judgments and Propositions. So I will draw out the distinction and talk about how we actually define a logic. What is a logic? How do we define it? How do we work with it? And things like that. And if you think about the Trinity picture that Bob drew, okay, so we had proof theory over here, and logic, and here we had type theory over here, and we had category theory over here. We can also think of this slightly different point of view. You can think of this as being mostly sort of the domain of philosophy, if you will. And of course, we know all of these things are connected, and this is computer science. And this is mathematics. And one of the reasons we're actually doing these kind of things together is to show that really they're all aspects of the same thing that we're trying to do. Okay. So today, in the first lecture, I'll stay mostly in this realm here, philosophy, logic, and proof theory, even though I will make some brief connections, I think, to the other topics. Okay. And then in the second lecture, I will talk about proofs as programs. And I reserve the right to adjust this lecture as I see what Bob's actually doing, okay? But I'm going to try to move a little bit into this direction, okay? So away from this into this direction. In the third one, I'll talk about proof search. And this is a very important topic, perhaps not so much because, I mean, there is a connection, of course, in this picture. On this side between proof search and sequent calculus. But also, if you use a system like Coq, then you're doing theorem proving, and when you're doing theorem proving, you need to understand how you search for proofs. Okay? And so it's very important to talk about the basic principle of proof search. You can use these kind of things effectively. So that's the third lecture. And I'm kind of still hedging my bets on the fourth lecture to see exactly what I'm going to do. What I did last year was something called focusing, and I might do that again. Or I might branch off in some different direction, talk about some other topics like monads and things like that. Okay. So let's come to the first topic on judgments and propositions. Okay, so Bob already drew out the basic idea, okay, that we have when we make a judgment, something like A is true. This thing here is a proposition. And the thing taken as a whole, that's what we call a judgment. And Martin Luther would say that a judgment is an object of knowledge. This is something that we actually know. Where a proposition is something in particular about which you make different judgments. And so we can think of other judgments to make about propositions besides the fact that they are true. Okay. So another judgment I'd want to make, for example, is to say A is false. Okay. That's a typical judgment that we often make about a proposition. Another judgment you saw this morning, okay, which is M is a proof of A, or equivalently to say that M is a program which has type A. Okay. So we know that by the connection between two poles on this triangle there, that these are really the same thing. That's another judgment. But now the interesting thing is that even in the realm of logic, there's many things that have computational relevance. And so the reason I'm going actually very slowly in today's lecture about the basic principles, how we define a logic, is because you will find yourself, if you're doing research in programming languages, sort of confronted with the task of perhaps defining a new logic or aspect of a new logic. And that's because you might be wanting to trying to capture new computational phenomena that haven't been captured in a logical way before. Okay. And so one way to think about this is, well, if we understand that triangle for a certain example, like intuitionistic logic, category theory, and functional programming, if you have other computational principles you want to capture, okay, what would this now look like? Okay, so in particular, so let's look at some basic examples from. Maybe I'll do it over there to keep up a little longer. Okay, from logic. Here is a particular one. So K knows A. Okay. Anybody happen to know what branch of logic is concerned with the study of this judgment? Epistemic logic. Anybody would want to hazard a guess what kind of computational phenomenon we may be able to capture with that? If we understand how to view the whole picture, okay, from a computational point of view, looking at epistemic logic. Distributed computing. Okay, so that's a computing where you have several nodes that each compute independently, and they can communicate with each other. Okay, so in the distributed computing sense, K here would be the nodes where things are computed, and A, in the way that Bob explained, is what is being computed. So it explains what, and this explains sort of where. Okay, so if you want to try to capture a good programming language for distributed computation, what you have to do is you have to study epistemic logic. Okay, if you want to do a good job. Okay. Okay. Here's another one. A is true at time t. Okay. Anybody know what kind of logic is concerned with that? Temporal logic. Okay. So what kind of computational phenomenon do you expect we would capture with temporal logic? Okay, so I've never been able to make that work. Reactive programming, question mark. Okay, homework assignment. Okay. By tomorrow, please give a complete system for reactive programming based on temporal logic. Okay. But actually, back way in 1995, a student of mine and I investigated this, and we came up with a different answer. Anybody happen to know this or want to make a guess? Okay, so it turns out to be, if you do this a certain way, a partial evaluation. Okay, so the idea behind partial evaluation is that at time 0, what you compute is not the final answer, but a program which will run at time 1. What you compute at time 1 is not the final answer, but a program which will compute at time 2. And eventually, you'll get something which is a value, at which point you're done. Okay, so that's the idea of partial evaluation. You don't evaluate the whole thing at time 0, but you evaluate up to a certain point. So if you just look at what the logic looks like, based on this judgment, A is true at time t, and then you extract from that a programming language, you get a programming language which performs partial evaluation. Okay. Then there's another example here. If you want to know about, if your judgment is something like A is a resource. Okay, and resource here, if you happen to know, I mean in the context of linear logic. Actually, I should write it here. This is linear logic. Okay. And then what you get, if you look at the programming language consequences of that, you end up with concurrent computation. There's more examples of that. Perhaps I will do 2 more, and I think at least one of them I'll actually talk about in one of the lectures. So that's why I'm going to bring them up. Okay. So one of them is A is possible. Okay. So, yeah, you have a question?
Is there really a one-to-one mapping between the ground of logic and the meaning. We were saying for temporal logic, there are two possibilities. For epistemic logic, I've been still working on encryption using this, and for linear logic, there are lots of use that are not perfectly consistent.
Right. Okay, so there's many different ways that logic can be used. The particular correspondence I'm talking about are the ones that Bob talked about earlier, where you view proofs in the language as programs. Okay, and that sort of nails you down within the space of possible applications. So there's a whole different branch of use of temporal logic, okay, which actually the temporal logic looks quite different from the one that I would write down, which is not intuitionistic, which is used to analyze in concurrent computation or programming languages. In systems like model checking, right? We have an imperative program, you write a temporal specification, and then you do some kind of proving or model checking of the computation of the concurrent program with respect to your logic specification. For that kind of thing, you usually use classical temporal logic rather than intuitionistic temporal logic. So it's a whole different kind of use of the same underlying logic. Well, actually, it turns out to be different underlying logic because one is classical, which describes systems. One is intuitionistic, which kind of defines systems. Okay. Other questions? Yeah?
So by computation, do you mean a setting where only one thing can have access to a resource at once, so like a lock-based comparison?
No, what I mean here is sort of like pi calculus. Okay. And of course, pi calculus as a notation for proofs might be a little bit foreign, so that you have to do quite a bit of work, and you can understand that certain pi calculus terms are notations for proofs. And if you want to do concurrent computation in that fragment of the pi calculus, then it really does correspond to linear logic and to the view of a proposition as being a resource. Okay. Sort of A is possible. Okay, actually corresponds to something. It's called lax logic. Okay, and the computational phenomenon is what you might want to call generic effects. And I don't have a column here for what happens when you do this algebraically, but it's called a monad. Okay, so if you want to think about a logic in which you can capture what a monad is, then what you need to start is from the idea that you have a judgment that A is possible, okay, rather than A is true. Another one is A is valid. That corresponds to a modal logic under certain interpretation of validity, and that corresponds to something which is runtime cogeneration. Or another way to think of it is you have a code construct in the language, and you have an eval construct in the language. Okay. Okay. So this is just to give you some examples that shows it's very important, okay, that many different logics can arise to capture various computational phenomena, and the way that we capture them is by appropriate judgments. Okay. And the kind of a notion of a proposition is somewhat parametric over which thing we're looking at. Now, if you want to capture and apply the ideas that I've given you in these first few lectures, you really have to understand in detail sort of how you actually define a logic. Because if you do it wrong, okay, then the logic doesn't really make sense, and the computational interpretation is off, and things don't really work together the way they should. Okay. So therefore, I'm going through this very slowly. Okay. Are there questions on these examples? I think I will probably talk about at least about this one, about the connection between possibility and monads. But there are references for all the other ones. Okay. So you can look these things up. Okay. Yeah?
Modal logics?
Yeah.
So is there a more specific term for that last entry modal logic? The validity logic?
Yes. Right. The particular one we're looking at is called JS4.
That sounds specific. That's based off S4.
Yeah. Okay. So modal logic is kind of a very broad collection of things, just saying that there's different modes of truth. And I think in my terminology, I would say there are different judgments. That's what I would say. So traditional logic is just concerned with the judgment of truth, or maybe with the judgment of falsehood. And in modal logic, one is considered with more refined notion of judgment, like K knows A, or A is true at time t. So in some sense, a lot of these, at least these four, are all modal logic of some form or other. Okay. Yeah? I will try, because what does the bottom right say? Runtime code generation, or a language we import and eval. Thank you. All right. Okay, so let's see if we can now start with a very basic judgment that A is true and get through kind of developing some of the principle that we would need if you wanted to try to one of these other logics. Okay. So, by the way, a lot of the material I'm going to talk about today goes back to some very basic work by Gensen. In 1935, okay, which is actually his PhD thesis, as he published as a paper, in which he defines a system of natural deduction, which is very, very close to what I'm going to talk about here in this first lecture. Then there is work by Dummett in 76, and then Martin Leff in 83, which are all sort of the same lineage of work, taking a little bit further, and I may refer to one or the other as I'm going along in my explanations. Okay, so the first question is, and I'm going to use conjunction as my first example because it's very simple. Okay, how do you find the meaning of conjunction? Okay, how do you find when? Okay, let's see if I can. How do you define when A and B is true? Okay, I hope this is large enough. You okay on this? Okay. And so, by the way, the parentheses on this, I'm not going to write this, but it's always, you have to read it like this, right? Because the thing on the left is a proposition, and this we write in postfix notation, it's a judgment on that proposition. Okay. So when should A and B be true? How do we actually define that? Okay. So one perspective, which we call the verificationist perspective, is I define the meaning of connective, but I'm telling you when this is actually, when you can prove that A and B is true. If I tell you all circumstances under which you can prove it, I therefore give you the meaning of what conjunction is, right? Okay. So I'll tell you how you can prove that. Okay, what's called an introduction rule, namely, I'm telling you can prove it if you know that A is true and you know that B is true. Okay. So on the one hand, this tells you the following: if A is true and B is true, then the conjunction is true. Okay. And on the second hand, I say every proof of conjunction should essentially be something like this, or you should be able to transform it or massage it or think of it as being something like this. So in some sense, I want to describe the meaning of it by telling you when it should be true. Okay. So the slogan here is that the meaning of a connective is given by its introduction rule. So this is a very important thought. So I'll just put it here. Okay. Okay. So this is what we call the verificationist. Verificationist. The meaning of a connective is given by its introduction rule, and in general there might be more than one, so we might have to say rules. Okay. So because I essentially telling you when it's true by when you can infer that it's true. Okay, so that's actually the first step. Okay. The second step we do now is how can we actually use the knowledge that A and B is true? So now we're actually turning it around, and we're asking, okay, if I know that A and B is true, what can I deduce from that? Okay, and that's called an elimination rule, because in this, I'm deducing something that doesn't have the connective in it. Okay. So what do we know if A and B is true? What can we deduce from that? A is true. What else can we deduce from that? B is true. Okay, so there's actually two elimination rules in this case. Okay, so let's argue why this is, if this is our definition of conjunction, why is this a valid rule of inference? Can somebody make the argument? Yeah?
There's nothing new you can prove if you start from
Proof of true and the proof of B is true using those rules.
Okay, so there's nothing new you can. Perhaps a slightly other way of saying it. If you know A and B is true, then we should have inferred it with this rule. Okay, so therefore A must be true. And if we have a proof of A and B, then it must have been essentially by this rule. So therefore, we should be able to know that B is true. Okay. So, so what we want to do when we check that these rules fit together, so that the elimination rules really are justified from the point of view of the definition of conjunction, is to verify if you can introduce the connective and then eliminate it again, we don't gain any information. Okay? Because otherwise the rule might be unsound. Okay. So this is called we call it a local soundness of the rule. Okay. I'll explain why local in a little bit, but we want to check that if you have a proof of A and B, A true, B true, and we conclude A and B true, and we apply to it an elimination and introduction. We apply to that an elimination. Okay, then there's already a justification for the conclusion. Okay, we already have a justification for the conclusion. And a justification for the conclusion is just a proof, right? So if we actually put some variables here to stand for the proofs, so this would be D, a proof of that, and let's call E a proof of that, okay? Then what is our justification for the conclusion? It's D, right? So we already have D, which is a proof that A is true. Okay? So this second rule is justified because the conclusion we have is already justified by a premise of the introduction rule. Now we have to check all possible pairs of introductions followed by eliminations, right? Because we want to make sure no matter how we introduce the connective, no matter how we apply elimination rule to the result, the conclusion is already justified, okay, when we start out. Okay. So we also have to check the other case when this is the second elimination. Okay. And then what's our justification of the conclusion? It's just E, right? Okay, completely. Okay, so this is, if you have checked both of these, that's what we call local soundness. And it's important to say what is sound here of the elimination rules. Okay? Okay. So let's go a step further. Okay. What we're doing from here to here is actually a proof reduction. Okay. Very similar to actually one that Bob showed, where he said the first component of this pair that we form is actually M. Okay. So this is actually a reduction, which is a reduction on proofs. So we have a proof that introduces connective and then eliminates again. We can reduce this proof. Okay, if our elimination rules are sound, we can actually reduce this proof to a smaller one. Okay, because we already have a justification for it. So another way to say that is that the local reduction, so this is called the local reduction. Okay, is a witness for the fact that the rules are locally sound. Okay. Because if I want to prove to you that it's locally sound, what do I have to exhibit? I have to exhibit some way of transforming a proof of an introduction followed by an elimination back to a smaller proof, okay, to show you that the conclusion was already justified. Are we doing okay here? Okay, you should interrupt me if there's questions because I think this should be very elementary. So, you have a question?
I have heard this wrong, but you say that local soundness is defined to be the local soundness of the local reduction.
Local soundness is a property of the elimination rules with respect to a given definition of the connective by the introduction rules. Okay. So the local soundness property is witnessed by a local reduction. Okay. So if you want to demonstrate to me that the rules are sound, what you have to show is how to locally reduce. Okay. Other questions? Yeah.
It depends on what the introduction rules are. So it's with respect to the specific.
Right. Correct. Okay. So what we're showing here is that we cannot gain any information with the elimination rules that we didn't already have, right? Because the information is already contained in the proof of the premises of the introduction rule. Okay. Okay, now the second thing is we want to, so basically this checks that the elimination rules are not too strong. So the elimination rules are not too strong. Okay. So, but what we really want in some sense is the introduction and elimination rules are in harmony. They actually work together more than just saying they're not too strong. We also want to know that they're in some ways complete. Okay? That they're strong enough, they're not too weak. So for example, okay, maybe I have no experience at all in designing logics. Okay? And maybe I forgot the second elimination rule here. Okay? I said, okay, this is my definition of conjunction. This is my elimination rule. Okay? And then, oh, let's check. Does it really make sense? Yes. We can always locally reduce. Okay? Still, this is a weird logic, right? Because the elimination rules are too weak. So intuitively, what's missing? Okay? We put some information into the conjunction. And if we only have the first elimination rule, we can never get it back out. You see that? Because we can't get back out the fact that B was true. So the elimination rules are too weak. Okay. So the question is, how can we check that the elimination rules are not too weak, that we've covered all our bases? So what we need is here some kind of check, okay, that the elimination rules are not too weak. Okay. And as you might guess, without knowing anything else, we call that local completeness. Okay. Now the question is, how do we check that they're locally complete? Okay. Anybody have an idea how one might do that? How can we check? I've got the second one. My only conclusion is A is true. And okay, so yeah, I think it's getting the right direction. So we want to start from the conclusion of all the eliminations. Anybody have another suggestion? Yeah?
So the introduction rules can be recovered through an elimination rule?
Each premise of the introduction rule can be an elimination rule. Okay. Okay, so that works for conjunction. We'll have to see how general that is. Okay. Any other ideas?
The premise of the elimination rules can be recovered using the introduction rule.
The premise of the elimination rules. The premise of the elimination rules, we know what that is, actually. What is that? It's always the proposition that's formed by the introduction rule. Okay. Okay, so we're going in the right direction. Yeah?
Given the proof of A and B, you can prove A and B.
Okay, given the proof of A and B can be proved. Well, that's almost what I'm, there's one proviso missing, yeah?
Did you define local soundness?
Yeah.
And what's the difference?
Okay. So local soundness under the elimination rules means that no matter how you introduce a connective, if you then eliminate it, you can already justify the conclusion from one of the premises of the introduction. Okay. That's the definition of local soundness. So now we want a similarly simple definition of a local completeness. Okay, so I think that, yeah?
So maybe you can prove A and B
Yeah.
from A and B, but without using the direct reflection.
Okay, so without using it directly, so let me reformulate that slightly. Okay. So arbitrary proof of A and B. We don't know what it is. Okay. And we want to be able to apply the elimination rules to it so that from the pieces we can reintroduce it. Okay? So we want to be able to apply the elimination rules. If the elimination rules are strong enough, we can get all the pieces that we need in order to reintroduce it. Then we know we got enough information out that we can prove it again, right? Okay, so let's see if that works here. So we have a proof D of A and B. So what do? Well, we apply the first elimination, and we get A true. And we take D, which is a proof of A and B, and we apply the second elimination. We get a proof of B true. Okay. And now from the pieces, we can reintroduce it, right? So now we can reintroduce it by AND introduction to proof of A and B true. Okay? So let me try to say it again, because this is very important. Okay? The question if the connectors are locally, if the elimination rules are locally complete, okay, means that they're strong enough so that we can take an arbitrary proof of the connective. We can apply the elimination rules in such a way that from the judgments that we get, we can reintroduce that. Okay. So what that will mean is that if you have an arbitrary proof, we can always transform it into one that ends by an introduction rule. Okay. So if you think about the introduction rule as defining what the connective means, it means no matter what kind of proof you have, yes, I can always transform into one that ends with the introduction rule. So it's okay as a definition, even with these elimination rules around. Okay? Does that make sense? Okay. So in this definition for the completeness, there's an existential quantifier, right? For the local soundness, we only had universal quantifiers to say for every way to apply the elimination to the result of the introduction, we can reduce it to one that already existed before. And here it says, okay, there is some way to apply the elimination rule so that from the pieces we can reintroduce what the original proposition. Okay? Are there questions on this? Okay, again, this is a very important part. Yeah?
Unique set of elimination rules for any introduction that
No. What happens is that you can design different elimination rules, okay, and they may perfectly work well, and what they actually mean in terms of programming language, you can use different primitives to define your programming language sometimes, okay. As long as the rules are locally sound and complete, okay, they should work together in harmony. That's harmony is actually a technical term. I'm not sure who introduced it, but it certainly appears in Dummett 76, but not originally in Gensen. Okay. So harmony means that the elimination rules are both locally sound and complete. Okay. And these are the properties that we have to check. Okay. Other questions? Yeah?
Intro rules, you would have to start with arbitrary proof of D and then end with a proof where the last rule and the relation with each one of the intro rules. Right?
Okay, we'll come to that when we come to disjunction, because there's several intro rules, so we'll have to figure out what happens in that case.
Okay.
Yeah. Yeah.
I'm still thinking about for soundness, you're using role modifier
check soundness, you have to check that any sequence of introductions followed by can be reduced, okay, to something that's already justified, right? Any introduction by any elimination. Because I want to show that you cannot gain any information at all, okay? With the local completeness, you just want to check that if I have an arbitrary proof, I can get one that ends in the introduction rule after I apply some eliminations. So there is a proof of that ends with the introduction rule. Okay. Up. So this thing here is called a local. And the local expansion is a witness for the completeness of the rules. It's called an expansion because you see the proof on the right-hand side is larger than the proof on the left. Okay. Okay, so interesting fact. Okay, just to give you some connection to programming languages. Okay, the first one up there, the local reduction, is just going to be this. If I have a first of a pair of m and n, I can reduce that to m. And if I have a second of m and n, I can reduce that to n. Okay, I will talk about that more in the second lecture. But just, you can kind of see what's going on there, right? Because you introduce a connective, which is like a pair of proofs. Then you extract a piece. And we already have that here when we take the first projection. Okay. Now, what does this local expansion correspond to? Okay. So what we have is we have an arbitrary proof of A and B. Okay. We can expand it to, okay, what is the right-hand side here? Anybody familiar enough with right, it's a pair of first of m, second of m. Okay. So the first part is related to the notion of computation because these local reductions actually form the basis for the computations in your programming languages. Okay, because you take the first or second component of a pair. So these are computation rules. Okay, so the second thing is more connected to properties of the values that we get out. If you have a computation of something that's a pair, which is a conjunction is, okay, then under some circumstances, okay, you will know that it's actually equivalent or will reduce to a pair of two values. Okay, that's essentially what this says. So when you get your value of pair type, you can decompose it. Okay. So this is sometimes called canonicity of values. So that's what this is related to, and this is related to computation. Okay. Okay, and of course we have just conjunctions, so things are very, very simple, but we'll start making them more complicated very soon. Okay. You okay on this? Okay. All right, so let's try to play this through for some new connectives. I think I'll put it here. By the way, another terminology that should be, that probably a lot of you know, is that the first set of rules, the local reductions, are called beta rules, and the second one are called eta rules. Yeah? That's right. That's your homework. Okay. And this time I'm not kidding. Okay, that really is your homework. Okay. So in that, this is called the pragmatist point of view. The pragmatist point of view is you define a connective by how you use it. Okay. And then the question is, how can you justify the introduction rules from that? Okay. And one of the recommended exercises for this evening is to work that out. Okay. Okay. So now I want to introduce implication, okay, which is a very basic connective. Okay, A implies B. The problem is, how do I define that A implies B is true? Okay. And I don't have enough concept yet in order to define when A implies B is true, unfortunately. Okay. So before that, I need what Bob called a consequence relation. which I call a hypothetical judgment, which turned out to be the same thing. So I need to find a way to actually derive what that is. Okay. Okay. So here's how I'm going to do that. Let's think of a small proof. There. So A and B and C is true. B and C is true. And elimination 2, and we get from that. Okay, so let's think about this. So what I've shown you here, what does it actually demonstrate? Anybody want to read out what I've actually shown you here? Is it a proof of B is true? Well, B is true is the last line, but B is an arbitrary proposition, so it couldn't very well be a real proof of B is true, right? Because right. What I've actually given you here is a proof under the assumption that A and B and C is true, right? So what happens here is that if you allow incomplete proofs with things that you actually haven't shown yet, okay, then you get what's called the hypothetical judgment, okay, or a consequence relation, okay. So if you write this in linear notation, you would write it like this: if I assume that A and B and C is true, then B is true. Okay, at the level of at this level of judgments. Okay, so these two things almost express the same thing, except that here I've given you a proof. They have only written down the judgment that's established by this little proof here. Okay. Okay. So with that in mind, okay. So let's go back now here. To prove that A implies B is true, okay, A implies B means I get to assume A and then I have to prove B. Okay, that's the normal mathematical meaning of implication. Okay, so the way I want to say that is I assume that A is true, okay, and then I have to prove from that that B is true. Okay. Okay, and so this would be the introduction rule for implication. Okay. Now I could also have written this one. A true turns out be true. And it turns out that in logic, traditionally this is a notation that's being used in the system of natural deduction, which goes back to Gensen, okay, because it is derived from this idea that you have a proof that's incomplete because there's something that you have assumed but not proven yet. Okay, you can see that from my example, this is a very natural way to write it. Okay, this is a way that's more appropriate for programming languages because when we label the assumption with variables, then it looks some kind of typing for programs. But we really is supposed to mean the same thing. So I'm going to go back and forth sometimes between these. Okay. Okay. Now there's a small issue here, which actually is very significant, which is that if I'm not careful, I can prove things like A implies B and A is true. Okay. Actually, maybe I even want to fix this to be A. Okay. And I shouldn't be able to prove that for arbitrary proposition A, right? Because A implies A, I certainly should be able to prove. But I shouldn't be able to use this assumption for proving this A over here, right? But, okay, if I can write it like this. By conjunction introduction, I have to prove A implies A is true, and A is true. So now I introduce my assumption A is true, and I have to prove that A is true. Okay. Well, these are the same, so I should be done over here. And then I just use this assumption to prove that thing over here. Okay. Which is something I'm not allowed to do. Okay. So the issue is that when I try to prove A implies B, okay, I can use the assumption A only while I'm trying to prove B and not outside of that subproof. Okay, so there's an issue of scope, okay, which you're familiar with in programming languages. So the way I'm going to do that is I'm going to label this assumption X and write the X over here. And I'm saying that the use of the assumption X is confined to this subproof. I can use it in the subproof, but not outside. Okay. Now, in the traditional logic literature, if you go back to Gensen and so on, you'll find that sometimes they use numbers here. This is like 1 and this is 1. Okay. But when you actually want to think about programming language terms, it's much simpler to think of these as being names, okay, or variables. And they need to be unique, so you don't get confused between different assumptions. Okay. I don't want to have more than one assumption called X, because then I don't know what I'm necessarily referring to. Okay. So this introduces a scope for X, and the scope is the proof of the premise. Okay. So if you do that here, this is AND introduction. This is implication introduction with X. This assumption is labeled X. And I can use that here to prove that A implies A. But I can't use it here. If I try to use it here, okay, then this is not a valid proof because the assumption X is only in effect up here and not outside the scope over here. So this is incorrect, and I have no way to fill in that. Okay. So very important to keep the notion of scope in mind. Okay. So that's the introduction rule. Okay. So the next thing we need to justify from that some kind of elimination rule. Elimination rule always asks, if I know A implies B, what can I deduce from that? Okay, so let's go back. If I know A implies B, I know that I have a hypothetical proof from assumption A to conclusion B. Okay, how can I use that? Yeah. Okay, so if I know A, then I conclude B. And that's the implication elimination rule. Okay. All right, so let's check whether this actually is sound and complete, right? That's always our job, to check that we didn't make any mistake in this rule. We can't deduce too much. Okay, so if I first introduce that, so if I introduce A implies B is true, by proving that B is true with some proof D under the assumption that A is true, label this X. This is implication introduction X. And then I have some other proof E that A is true. Then I conclude that B is true by implication elimination. Okay? Okay, so now I need to find another proof of which judgment here? Local reduction. I'm trying to verify that the rules are sound. What do I need? I need a proof of? I need a proof of B is true. Okay? I need to justify that B is true without introducing the implication, then eliminating it. How do I get the proof that B is true? How do I get the proof that B is true? Yeah? Okay? So from E, I get a proof of A is true. And then I had the assumption that A was true. So now our notation is a little bit weird. And I had to prove D, which shows me that B is true. Okay? So another way to think about this is substitution. Okay? In this proof, I use X perhaps multiple times. Okay? And the X is the assumption that A is true. Okay? And now I actually have a proof that A is true, and I substitute that in at every place where I use that assumption. Okay? So this is my notation here. Maybe I should duplicate that. So this is substituting the proof E, okay, for uses of X. In D. Okay? Yeah?
Is there a risk of ambiguity if you use E as the rule name instead of using X as the rule name?
Could you say it again? What's the ambiguity?
If you use E as the name of the axiom, A true.
Okay, so E actually stands for proof.
Yeah. But now it seems like X is out of scope.
No, X disappears. The proof no longer depends on X because I have substituted E for it. So it's sort of like the counterpart of this will come to in a second. Okay, actually, let me do that. Okay. So this proof here, in the notation that Bob introduces, will be X is a proof of A that D, if I'm going to use the same letter, is going to be a proof of B, right? Okay.
So that actually is a binding occurrence here?
This X here in this rule is a binding occurrence with this scope. And so when I substitute for it, it disappears. So in this proof, after substitution, X is no longer there.
Okay, yeah, I guess my observation of it kind of disappears. I still see it, but I understand it's not really used.
Well, okay. So what you have to do is when you do the substitution, you create out of the substitution a new proof. Sort of just like when you write, okay, so actually let me finish that example here. So then we also have E is a proof of B. And from those two things, we get that, what would it be? E is a proof of A, right? That E for X in D would be a proof of B. Right? So this denotes an operation of substitution. Okay. And so this gives you some term that doesn't use X anymore. And this is just another clunky way of writing it.
So it might be clearer if the clunky way of writing it didn't
But that doesn't read.
I need to translate this notation to something here. I need to substitute the assumption X. Okay. So I can't get rid of the X entirely. So these script letters, they need to know proof. I'm sorry, I didn't quite hear that. Yeah. Right. Okay, well, actually, we also write it next to it, but that's not traditional way because a proof is sort of two-dimensional going up on the board. At the moment, but look over there. So it's very important. I mean, okay. If I were lazy, I said, okay, in today's lecture, the judgment is only true. I don't have to write it. Okay. But I want to be careful because you have to be careful about that because there's different situation, and then the judgment is different, and then everything changes. Okay, so I'm just being pedantic. Okay. Does that make sense? Okay. So and maybe you can kind of see the connection that this substitution is just this. Okay. Okay. So we also need to check the completeness, right? Actually, I can do it here. So I assume I have some arbitrary proof of A implies B is true. Okay. How can I apply, or actually can I apply the elimination rules so that I can reintroduce a connective from that? Okay, so I'll have that proof D of A implies B is true. Okay, and I need to apply some elimination to that, right? Elimination, following our nose here, would say, okay, this has to be an elimination. I don't have a proof of A. What do I do? I assume it. Okay. A true. Let's label that assumption X. Okay. And then I get B true. And then I can reintroduce it to prove A implies B true. Okay? So now read from bottom to prove A implies B. I assume A, and then I have to prove B. Well, I have a proof of A implies B, so now I can apply the elimination rule with this new assumption to get my proof of B back. Okay. Okay. And so this is our expansion. Okay. Okay. Actually, let me do proof terms because we're getting very close to having them anyway. Okay. So if you want to rewrite these rules using proof terms, Okay. All right. So the thing up there, okay, is very easy. M colon A, N colon B, then the pair M, comma N, or colon A and B, and then it's M colon A and B, then first of M is a proof of A, and the second one, of course, exists as well. Okay, and then the local reduction is just first of the pair Mn reduces to N, M, and the second of the pair Mn reduces to N. Okay, so now we need to introduce for the proof term notation for the lambda abstraction. I mean, for the implication, it's going to be lambda abstraction, so it's going to look like this. So I have, okay, under the assumption that X has type A, I can prove that M has type B. Okay, though that's just sort of the same it's a different notation for the same thing that I have here. Okay, and I name the proof term, and then I have that lambda X M proof of A implies B. Okay. And there's some question about whether I should put the proposition A in here into the term or not. I don't want to get into this discussion right now. So this would be the proof term. Okay. And then the one for implication elimination would be like this. If I have M is a proof of A implies B, and N is a proof of A, then what's the proof for B? M applied to N, right? Because M is going to be a function, and so I apply to an argument. Okay. And then the reduction is going to be, if we just take the picture over there and we write it down, lambda X dot M applied to N reduces to, okay, N for X in M. Okay. And the question is, what is the expansion? So the expansion over here says if I have a term M of type A and B, then I can expand it to the pair first of M, second of M. So what's the expansion over here? Well, I have to start with M of type A implies B, which is the same as a type of a function from A to B. Okay. And what do I expand it into? Okay, so now we have to see what's the result of where's the expansion? Is it still here? Here it is. Okay. So this corresponds to the M. So can anybody read off what the proof term for the thing on the right would be? Okay. So we introduce an X. And then, what is the proof term for the implication elimination? Apply M to X, right? Okay, let's write it in over here. So this is M is that, X is that. Then by implication elimination, this is M applied to X. And so this becomes by lambda X dot M applied to X. Okay. So this is what's called an eta rule. Okay. And usually it's thought from here to here as an eta contraction or eta reduction, and from here to here as an eta expansion. Okay. So M is related to lambda X, M applied to X. If M is a function, that should be okay. Right. You see that the two things should be the same in some sense, because if you take a function M, you apply to some argument, you get M applied to that argument. If you apply this to some argument, you get, after one reduction, you get M applied to that argument. So if you apply them to something, these two things behave the same way. Okay. So that's another way of saying that these eta rules are related to extensionality. Okay. Because under application, these two things will behave the same way. And this is related to computation. Okay. So that's another way to distinguish those two from each other. Okay. All right, and we need as a primitive kind of this notion of substitution, okay, which comes from the notion of proof substitution for hypothetical judgments. Okay. Are there questions on this? So we're doing pretty well, which is not surprising because, of course, intuitionistic logic has been understood for a long time. But when you want to design your own logic to capture some computational phenomenon, you find it's not always that straightforward. Okay, it takes a significant amount of work. The reason is that when you have more than one judgment involved instead of just true, then things get more complicated, and you need to figure out how to put the pieces together in the right way so that they still all make sense. Okay, so even though at some level this may seem trivial, okay, it's very important to follow the right strategy and to make sure that when you do one of these things that you follow that strategy and sort of check these properties very carefully. Okay, other questions? Okay, let's do a few more connectives. Okay. So I'll do disjunction. Okay, so now we just want to play through what we've learned, okay, to define new things. So I want to define A or B. Okay, when should A or B be true? What is the meaning of A or B? Yeah? Right. So we have two introduction rules. Okay? Because there's two ways that a disjunction could be true. Either the thing on the left could be true or the thing on the right could be true. Okay? All right, so now we need to figure out what the elimination rule is. So if we know that A or B is true, what can we deduce from that? So here's a straw man. Okay? I'm going to try to prove that A is true from that. Okay, you should be very suspicious. Okay. Now, how do we find out that this is wrong? Yeah? Okay, so I'm going to do it without using implication. I think what you said was right, but I want to do it without implication. Yeah?
You would get back new information.
You get new information.
Yeah.
Okay.
So you start from B true, you start from A true.
A true.
And from that you deduce A or B true. And then you use this rule to get back B true.
Okay, so the way I can reduce that, okay, because the conclusion is not justified by the one things I already have. So that rule is not sound, okay? So with conjunction, I made a mistake when I left out the second rule because now the rules are not complete. With disjunction, if I write this rule, I make a mistake because this rule is not sound, because I could deduce things that actually shouldn't be true, okay? Okay. Surprisingly, though, a lot of students try to make this inference anyway, okay, in an introductory logic class, okay? But, okay, so it's not sound. Okay, so how do we proceed? Yeah?
That A is true, you can prove C.
Okay.
And likewise, under the assumption that B is true, you can prove C. You can prove C.
Okay. So, the assumption is A is true, prove C, and B is true, we can prove C, and then we can prove C. Or elimination. Okay, so now we need to be careful about the scope. Okay, what's the scope of this assumption that A is true? is just this proof here, right? So let's call this X, right? And this is the scope of X. And this assumption here, this is the scope of Y, right? You cannot use things outside their scope, right? So what this says that if I know A or B and I'm trying to prove C, then I distinguish the two cases. In one case, I'm allowed to assume that A is true and I have to prove C. In the other case, I'm allowed to assume that B is true and I have to prove C. And if I can prove both of these, then I'm allowed to conclude C. Okay. Okay, so this is a little weird. Okay. So the strange thing that we haven't seen before is that we need to introduce a new proposition C, which is not inside what we're trying to prove. Okay. Now, as far as I know, there is no good way of writing this down without doing that. Okay. So we need this extra proposition that tracks what we're trying to prove. Okay. So we should check that these are sound and complete. Okay. So how do we check that it's sound? So remember, any way of introducing followed by any way to eliminate, we can actually reduce it. Okay. So let's try this introduction by this elimination. So we have A true, A or B true, and then here we have A true, X, C true, and here we have Y, B true, C true, and we conclude C true. Okay. So let's give these things names. So this proof is D, this is E, and this is F. Okay. If it's sound, we should be able to find a justification for C without introducing the disjunction and then eliminating again. So how do we justify C? Right. So we accounted for the case that this was A is true by giving this proof here, this case, the proof for that case. So now we can get the conclusion C true by substituting this proof up here. So it's something like D for X, which proves A true, and then we have E, and then we prove C true. Okay? So for disjunction also, okay, we need to do a substitution, okay, in order to show that this is locally sound. Okay? If this was the second OR introduction, where we use B true, what do we do? In that case, we substituted for Y in this proof. Okay? That's why we gave both cases, because we don't know how we use what we use to infer that. Okay? Okay, good. So it's locally sound because any combination of introduction followed by elimination can be reduced. Okay. Now we also need to show that it's complete. So now I'm coming back to somebody's question earlier on. Okay. So let's assume we have a proof of A or B. Okay. So the question here is what we're asking, is there a way to apply elimination rules to it so we can reintroduce a connective from the pieces, right? Can we get all the pieces out? So how do we do that? Yeah? Right. Okay. So we have D prove A or B. We apply the elimination rule. Okay. And so in the first part, we get to assume A, and we call that X. And here we get to assume B. We call that Y. And here we use the first introduction rule to get A or B. And here we use the second introduction rule to get A or B. And so at the bottom here we get A or B. So something important about this is that we're using the fact that this can be an arbitrary C here, because we're using it for one specific one, namely A or B. Okay? So this really must hold for arbitrary proposition C, okay, in order for this to work properly. Okay. So what's a little odd that, and again, this is kind of a problem with the syntax for these deductions, is that it looks like the elimination rule is below the introduction rules. Right? But if you think about the way you construct the proof, you apply the elimination rule first, and then in the two branches, you actually use the two introduction rules. Okay? So it really is applying an elimination rule to something that you know, and then reintroducing the connective, in this case, in each branch. Okay. I think that should answer the earlier question about what's going on in this case. Okay? All right. I kind of promised Bob that I would do negation, so I need to do a little bit more. Okay. Let's see, when did I start? Should I have like 20 after or something like this? Okay. 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 So the next thing I want to do is falsehood. Okay. Falsehood is related to negation, and there's different ways of doing it, but I'm just going to try to do it this particular way. I'm trying to define when is falsehood, and this is written sometimes red bottom. Okay. When is falsehood true? Okay. So what are my introduction rules? There are none. So no introduction rules. Okay. When I actually write these things on a piece of paper when I present the logic, I always write this, okay, explicitly. So it's not like I forgot to write it down, but there isn't one, right? And so if you don't write it down, sometimes people think, oh, he forgot. What's the introduction rule for falsehood? Okay, no, there is none. Okay. Because you shouldn't be able to conclude falsehood, obviously, okay, because it means it's never true, so you shouldn't be able to infer that. So my definition is that it has zero introduction rules. This is actually the nullery case of disjunction, right? Disjunction has two pieces, so therefore there are two introduction rules, right? Okay. Falsehood has zero pieces, so therefore there are zero introduction rules for it. Okay. If I had A or B or C as a primitive connective, I would have three introduction rules, right? Very simple. Okay. So what is my elimination rule? Okay. So let's do it by analogy over there. If I know that bottom is true, okay, what can I conclude from that? Okay. C is true. Okay. Because I have accounted for all possible cases in the proof of bottom, right? Because there are none. Okay. If I had a disjunction of three things as a primitive connective, I would have three introduction rules, and here I would have three premises that account for the three possibilities, right? If I have zero introduction rules, I have zero cases to account for, so I go from bottom is true to C is true. Okay. So basically it says if I have derived a contradiction from my assumption, I can conclude anything. Okay. Okay. So that's, we should check that it's locally sound and complete, right? We always should do that. Okay. Okay. So any introduction rule followed by the elimination, can we reduce it? Well, how many possible cases do we have to check? None. Okay. It's sound. Okay. Now, what are the computation rules associated with that? None. There's no computation rule, okay, because there can't be any proof of that. Okay. So no computation rules. Now, what about the local completeness? Okay. So we have to show if you have an arbitrary proof of true. Okay. What does that mean? So we somehow can apply the elimination rule so that from the pieces we get, we can reintroduce it. Yeah? Right. We have that. So we use bottom elimination to conclude that. Okay? So this is using this elimination rule here by using bottom for C. Okay? And we have reintroduced it as many times as we have introduction rules. I mean, we have reintroduced the connective 0 times. Okay? This is exactly the analog here. Okay? So if we have 2 introduction rules, we eliminate it, and then in each branch we use the 2 introduction rules, and then we conclude that. If you have 0 components of the disjunction because there's no alternatives, and this is going to be bottom, there's nothing here, and we conclude bottom. Okay. So there is an extensionality principle associated with that. Okay, to go from this to this. Okay. All right. So I guess to finish the lecture, I was going to do something else, but my original plan. But let me finish the lecture. Just one remark about negation, and then okay. Let's one remark about negation. So the question is, how do we define not A as true? Okay. Okay. So we could go through, okay, and try to define it by introduction elimination rules. Okay. But there's another way to do it, a different style of definition. We could say this is equal to A implies falsehood. Okay. So that's what's called a notational definition. Okay. So we say negation isn't really first class. Okay. But where you see not A, replace it by that instead. Okay. And part of the homework exercise you can do, okay, is to actually see, if you don't want to do it this way, but you want to define it directly by introduction elimination rules, what that would look like. Okay. How you would define not A. Okay. But typically, in order to limit the number of things that you actually have to define explicitly, if there's some way to build it out of the connectors you already have, sometimes it's convenient to do that. Okay. And not actually try to give directly introduction elimination rules for it. Okay. Okay. Does that make sense? So we have 2 ways to define what a connective means. One is by notational definition. Okay. So we see not A, replace it by this. Okay. And the other one is by giving the introduction rules for it and then deriving what the elimination rules would be and showing that they actually work together. Okay. I wanted to show the proof term assignment for disjunction and contradiction, or to finish the lecture. Okay. And then in the next lecture, so some of the topics that I had thought to cover, actually I'll spill over into the next lecture because I pulled some other things forward. Okay. So actually maybe I can write it in here. Okay. So if M is a proof of A, okay, then basically what we have to say here is something like we have to give some indication which of the 2 sides of the disjunction was being proven by M. So we don't build a pair in this case because we have only one premise. And this is INL for injection on the left of M has type A or B. And if M is of type B, then this is injection on the right of M has type A or B. And then for the elimination rule, it looks like this. If M is of A or B, then X colon A, N has type C, and X colon A, P has type C. And then the proof term for Y colon B, yes, thank you. Okay. So then the proof term here is going to be, we take a case of M, and there's 2 possibilities for M. It could be an in left of X, and then we behave like n. Or it could be an in right of x, in right of y, and then it behaves like p. And so this would be the proof term there. Okay? And the reduction, okay, would look like this. If we have a case of an in left of m, and the possibility is in left of x, arrow n, or in right of y, arrow p, okay, then what does this reduce to? What does this reduce to? Okay, so remember what we did in the local reduction? I think it might still be up there. We did a substitution of proofs, which turns into a substitution of terms. So what substitution do we have to carry out here? M for x and n. Okay, so actually it turns out to be some kind of pattern matching, right? So if it was injected into the left part, okay, let's check the types here. This whole thing here is of type A or B, right? And so M is of type A because we're injecting into the left. So this is of type A, right? And so here in this branch, we assume that X was of type A when proving that N was of type C. So we can substitute M for X because M has indeed the type A. Okay, so that's a way to think about checking this. And then there's a symmetric one. If this was an in right, then this becomes substituting of M for Y in P, right? Just the other case. Okay, what about the computation rule for bottom? Okay, so I need to give you proof term notation. So no proof term here. If M has this type, then this is called abort of M is a proof of that. Okay. So let's see what happens here. If we have M is of type bottom, okay, then what is the proof term that we associate here? What's the proof term with that? Well, this is M. And what's the proof term down there? Well, it's abort of M, right? Okay. So what the expansion says is if you have an M which has type bottom, which is a proof of a contradiction, then you can expand it to abort of M. Okay. So that would be the local expansion. Okay. What's the local expansion for A or B? If M has type A or B. Okay. So is the expansion up there? It's here. So we just have to read the proof term off from that. What would be the proof term? What would it start with? Case. So we do a case of M of in left of X, and the other possibility it's in right of Y. Okay. What do we put here? What is the proof term for that? What's the proof term for the first part here? Yeah. We inject again into the left. And what's the proof term here? In right of Y. Okay. So if we have an M, then it has to be an in left or an in right, so to speak. And so if we take a case over that, if an in left, we reconstruct it. If it's an in right, we reconstruct it. Get the same thing out again. Okay. And then you see that this thing here is just a zero-array version of that, because this is a case of M with no alternatives, so there's no other branches. So we reconstruct it 0 times. Okay. Which is kind of an odd special case. Okay, questions? Okay, so what we'll do next time, We'll think a little bit more about the computational interpretation. And one of the things that I want to do is to actually go beyond the pure intuitionistic logic, where the only judgment of interest is truth, and introduce some other judgments. And I'll have to decide exactly which one that is. I definitely want to talk about possibility, because I think, as Benjamin mentioned, monads are going to be important in various lectures in the summer school. So seeing them from the logical point of view might be helpful. And I might also talk about this interpretation of validity. We'll see how far I can get. Okay. No more questions? All right, thank you.